Okay, so the stuff that we did at the beginning of the year, I thought was kind of stupid at the time, but honestly, it does provide a good foundation for the class. Okay, so you remember, right, what a system is from like physics. The system is just anything that we care about. My system could be this cup of water. My system could also be just the water in the cup. That means if the water were to boil, then my system would actually be all of the water vapor still. In the case of this cup, then once the water boils, then there's just no water in the cup anymore. So I would say, oh my gosh, the mass of my system just decreased because there's no more water in there. And this gets into properties of the system. You might remember this from like middle school science, but there are extensive and intensive properties. I like to remember that extensive properties care about the extent of our system, aka how big our system is or how many molecules are in the system. This could be something like the mass of our system. Intensive properties, I like to think of it as you can just grab a handful of your system and you can say a fact about it. Like I can grab a handful of water and I can say, I don't know how many molecules this is, but I do know that it's about room temperature. So intensive properties could be things like temperature or density. Side note, a dimension that you might not have known yet is specific volume. I didn't know before this class. So what you think of as volume, like meters cubed, so that is just total volume of the system. Specific volume is lowercase v, and it's measured in meters cubed per kilogram, which also means that specific volume is 1 over the mass density. And you might be like, okay, but what does this actually mean? How is this helpful to us? And it took me like a month to understand, but basically we're saying if I have 1 kilogram of water, then how much space does it take up? This is really good because we've changed an extensive property into an intensive property. I can take a handful of water and say, okay, I don't know how much volume this takes up, but I do know how much volume 1 kilogram of this water would take up since I know that it's at room temperature and atmospheric pressure. We also have these two variables to measure the energy within a fluid. This is just the internal energy, and then enthalpy is just that internal energy component plus pressure times volume. Basically, anytime you're working with a system where the volume doesn't change, we can just use this for energy. But anytime the volume does change, then we will have to use enthalpy to describe the energy of the fluid. Cool, so you know what properties are. States are just something that can be explained by the properties. This will make more sense later, but basically like this could be state 1 and this could be state 2 of our system. It went from this to this. Each of these states can be uniquely described by their properties. The process is how we went from this state to this state. And if I had another process going back here, then we would call this a cycle because it starts and ends on the same state. Just some quick vocab terms, we have 3 types of systems: open, closed, and isolated. In open systems, we're allowed to have mass transfer at the boundary and energy transfer. This could be something like just part of a pipe. We have water going in, water going out, and that water itself has thermal energy, so there's energy and mass crossing the boundary of our system. In closed systems, we are not allowed to have mass transfer, but we can have energy transfer. This could be something like a cup of lemonade when it's outside. There's thermal energy going in, but we assume that none of the lemonade starts evaporating out. In isolated systems, we're not allowed to have mass or energy transfer at the boundary. I like to think of just like a really good thermos that over time, the temperature doesn't change and the mass doesn't change. Okay, finally we get into some real thermodynamics. We're going to talk about ideal gases. For ideal gases, pressure times volume, this is total volume, so meters cubed, is equal to N, which is the number of moles, times this constant R times the temperature. This can also be written as PV equals RT, where this is specific volume and this is specific gas constant. Specific gas constant is specific to a specific gas, like maybe like hydrogen or something, where we say, okay, let's take our gas constant and divide it by the molar mass. There's also this other equation, Van der Waals equation, where you just have these constants A and B. I forget when we use it, but like you would know. There's a bunch of other equations that I'm not going to show the full derivation for, but these are just some other cool things that you can use. These letters here are specific heat capacities. Cp is equal to the partial with respect to temperature of specific enthalpy, meaning that we're at constant pressure. And Cv is equal to the partial of internal energy with respect to temperature, which means that we're a constant specific volume. The reason we have these is because sometimes we just use these equations, but it's honestly not very precise and we don't use it very much. We also have this thing called compressibility, which is PV over RT, and compressibility is Z. So for ideal gases, Z would be 1 because these things should just be equal to each other. You kind of just have to judge how ideal is this gas and can we model it as an ideal gas based off of how close this number is to 1. We also have these things called reduced values, which are just dividing by the critical temperature and the critical pressure to get reduced temperature and pressure. The reason we do this is that you can kind of analyze it as whether it's hydrogen or water, these kind of equal the same numbers, that you can compare them relative to each other. Moving away from ideal gases for a second, we have this thing called the liquid approximation. The liquid approximation basically says if we have a compressed liquid, we can just say that it is a saturated liquid at that same temperature. Let's look at TV and PV diagrams. This is what we call the vapor dome. So if your temperature and specific volume, or it's over here, then you know that it's a liquid. If it's over here, then it's a gas. And if it's inside the vapor dome, then it's some mixture of the two. This literally means that if I had a cup of water and the temperature and specific volume were within here, then there would just be some water in the bottom and some vapor on top, and it would never fully settle. It would just always be at some proportion of the two. We express this in a value called quality, which is basically just the percentage of it that is vapor. So if quality is 1, then we know that it's right here because 100% of it is vapor. And if quality is 0, then it's right here because 100% of it is liquid. If quality was 0.5, then we would be somewhere in the middle. PV diagrams will also have the vapor dome in them. Since T, V, and P constitute a multivariable relationship, we can't show all of it on a two-dimensional graph. So what we're going to do is we're going to use level curves. Level curves basically mean that at this height or at this temperature, then this is what the function looks like. We could say this is temperature equals like 100 degrees Kelvin. For TV diagrams, the level curves are going to be in terms of pressure, and they're actually going to go up this time. So this could just be like pressure is equal to 10 kilopascals. Now that you have a sense for kind of how the variables interact with each other, let's start talking about heating and work. Heat and work are two ways that we can change the energy of our system. Heat is Q, work is W, and both are measured in kilojoules. As I think I mentioned earlier, when volume is not changing, the way we're going to talk about the energy of the system is internal energy, or capital U. Therefore, we can say that the internal energy of the system is just equal to the heat plus the work, and these terms can be positive or negative. This equation is known as the closed system energy balance. Heat's pretty straightforward. If I put it on a stove, then heat is positive, and if I put it in a refrigerator, then heat is negative. Whether work is positive or negative is actually a little bit more complicated. Work in is when W is positive, and work out is when W is negative. Something that could be work in is if I took my hand and I just compressed a bunch of gas. I'm adding internal energy to the system, I'm adding potential energy to the system, but then work out would be like if I relax my muscles and let the gas just move my hand up. My hand had to move up somehow. It wasn't because of my muscles, and it's because work left the system. Energy left the system to raise my hand. We have this integral equation to express work when you're compressing a gas or expanding a gas. There's a bunch of vocab terms that we use alongside this, like isothermal is when temperature is being kept constant, and isobaric is when pressure is being kept constant, but I don't think they're really that important to look at. It's just like if you knew that pressure wasn't changing, then you could take it out of the integral. If you knew that the volume wasn't changing, then this integral would be equal to 0, etc. We have this one specific instance called a polytropic expansion or compression, where this quantity P, V to the N is not changing over time, and we can express the work out using this equation. Okay, so we talked about closed systems where mass is not entering or leaving, but now let's talk about open systems where mass is allowed to enter or leave the boundary of the system. Finally, we have the open system energy balance, which says that the change in internal energy over time is equal to the heat in plus the work in plus the mass flow rate in, that's like kilograms per second, times the enthalpy of the incoming fluid, plus kinetic energy, all the energy terms, minus all of these terms, but coming out. Once again, I just like to imagine part of a pipe, so we have water going in and water going out. A lot of times we make the assumption that the open system is operating at steady state. We don't assume that the pipe is just getting hotter and hotter and hotter. We can still assume maybe that it's coming in at 500 degrees Kelvin and exiting at only 300 degrees Kelvin if there's some process going on in the middle. Maybe I have something really cold, so some heat is coming out over time. But we would still assume that this is at steady state, meaning there's a constant amount of heat coming out of it over time. This means that our change in energy over time just goes to 0. Also, a lot of times we don't care about the kinetic energy or the gravitational potential energy just because these are a lot smaller than the thermal energy. Steady state also means that the same amount of mass is coming in as coming out, because otherwise you would just have mass that accumulates in here, or eventually you'd have no mass. So a lot of times our open system energy balance just looks like this, where we talk about the change in heat, the change in work, and also the mass flow rate coming in or out, because it should be the same, times the difference in enthalpy from the start to the finish. Okay, now that you understand closed and open systems, let's talk about some different applications of these. And this comes in the form of cycles. Okay, so there are 3 main different cycles. The first we're going to talk about is power. So this is generally what a power cycle looks like. So we have this heat exchanger where heat's coming in. This is like when you burn coal to boil water. Then it comes here to this turbine, which generates some electrical power from the thermal energy of the water. It comes down here to a condenser where some heat comes out, and then it comes here to a pump where it's pumped back down to a pressure such that this can keep operating at steady state. Obviously, we assume that this amount of work is a lot more than this amount of work because we want to generate a net positive amount of energy in a power cycle. We also have this thing called the refrigeration cycle, which is actually also the same as a heat pump cycle. It just depends on your goal, where work is being put into the system in order to move heat out of something and into something else. So like in a refrigerator, this would be like your jug of milk. Heat is being taken out of it and put elsewhere. For a heat pump, it would be the exact same, except now this is your goal. Your goal is to put heat into something. We have these three values here to tell us how good our cycle is. So this is our thermal efficiency for a power cycle, and it just tells us the proportion of the work out to the amount of heat that we had to put in. This number is always going to be less than 1. We also have these values here that are the coefficient of performance for a refrigeration cycle and a heat pump cycle respectively, and they just tell us the ratio of the amount of heat that we're able to move to the amount of work that we had to put into the system electrically. Now we're ready to talk about this thing called the Carnot cycle, where everything is ideal and no entropy is created. We'll talk about that later. But basically, as it turns out, the thermal efficiency and the coefficients of performance can be analyzed purely from the temperatures of the different heat banks. So like the temperature at the condenser and the temperature at the heat exchanger can tell you the exact thermal efficiency of a power cycle. And similar things can be said for these. They're just the temperatures of the different heat banks. All right, before we get too far into this, let's talk about entropy. So entropy is measured in kilojoules per degrees Kelvin, and unlike energy, this actually can be created out of thin air over a process. We have these three statements that kind of explain entropy. We have the Clausius statement, which says that heat will never spontaneously move from a cold reservoir to a hot reservoir. The Kelvin-Planck statement says that you can't have a process that's just Q in and then generating work. And we have the entropy statement, which, as you might already know, entropy at the final can't be less than entropy at the beginning. So entropy is capital S, and specific entropy is lowercase s, which is per kilogram. But then we also have this thing called entropy production, which is in sigma, which is basically a change in entropy, but it just tells you how much entropy was created out of thin air over a process. This is our closed system entropy balance, which says that the heat at some temperature boundary, if you add all of them up for a cycle and then add the amount of entropy produced, that'll tell you your change in entropy for the process. We also have our open system entropy balance, which says that the change in this over time for our open system is equal to the change in heat over the temperature boundary, the mass flow rate from the incoming entropy minus the outgoing entropy, and the production of entropy over time. We also have this equation to add to our ideal gas equation, which says that the change in entropy is equal to the change in entropy superscript O minus gas constant R times the natural log of the second pressure over the first pressure. Okay, so we have this idea of a normal turbine which takes in some enthalpy and then puts out some enthalpy of water to generate work. But then we also have the idea of an isentropic turbine, which basically says that there's no entropy produced, or sigma is equal to 0. We can express how good our in real life turbine is by talking about its isentropic efficiency, or how close it is to being perfectly no entropy created. We have these two equations. This is isentropic efficiency of a turbine, and this is isentropic efficiency of a pump, basically where this made up state 2s has the same amount of entropy as 1, meaning no entropy was produced over this process. Later in the year, we just talked about more practical outputs, like you could have a cogeneration power cycle where it's both a heat pump and a power cycle at the same time. You're generating power and you're heating a building. You could also have something with like reheat where it goes back into a thermal reservoir before going out to more turbines, or you could have something like regeneration where it preheats the steam before it's even heated, which reduces the net output of work, but it does increase the thermal efficiency. But I don't really think that we need to talk about it much because we move out of the theoretical world and into the real world, which just takes a lot of time to understand and doesn't really come across in this video as well. But yeah, that's basically everything you need to know in thermodynamics. As you can see, there's really only a couple things. You just have to be actually fast at analyzing it to like do well on a test. But overall, it's just like a couple different processes, a couple different variables, and you just move them around for different questions. So cool, that's thermodynamics. There you go.